We will continue with our discussion of transformers. In this lecture, I shall show you some interesting experiments and analysis relating to transformers, including three-phase transformers. We will just have a quick review of what we have done already. For an ideal transformer, the equations which govern the behavior of the voltage and current are in fact written down here, and for an ideal transformer, remember that the flux phi 1 is equal to phi 2, and as a result of which we will have V 1 by V 2 is equal to N 1 by N 2, and of course, the mutual inductances and the self inductances are related in a certain fashion. Now, remember that in this figure we have in fact the currents, in fact all throughout this lecture I will be taking the direction of currents flowing into the dot here, and remember that the voltage is the potential difference of the top point with respect to the bottom point, that is the where the dot is and the other side of the winding. Okay. So, the voltage is measured from the side in which there is a dot with respect to the side which is the end of the winding which is not at the dot. Okay. So, this with this convention you have these equations, and if you further move on, if we talk of an ideal transform which is operating in sinusoidal steady state, in fact we can take in get some more interesting relationships. In fact, if we assume that not assume that, in case we keep the transformer open circuited, it is very clear from this equation that the open circuit current, that is the transformer secondary is open circuited, the open circuit current is V 1 upon j omega L11. V 1 bar of course represents a phasor. So, we are talking of sinusoidal steady state in the same sense as we understood sinusoidal steady state in the first 5 or 6 lectures which we took as a part of this course. Now, in case we load the transformer, so now we are talking of a distinctive condition. We saw in the previous lecture that you could really write the first equation as is being shown there in the slides, and as a result of which you will find that your currents, in fact V 1 will come out to be equal to j omega L11 into this is I 1 load plus N 2 by N 1 I 2 load. Now, remembering that under open circuit conditions V 1 is equal to is related to the open circuit current on the primary side, what we see is of course that we come to get this relationship. Okay. Now, of course, if IOC is negligible, then the relationship becomes even simpler, but of course, if it is not negligible, we are back to having IOC appearing in the equations. So, this is the very fundamental relationship of a transformer. It is of course valid under steady state conditions, because we could actually substitute quite easily for V 1 and we could in fact write down these equations quite easily, because in sinusoidal steady state we can replace the algebraic equations here by simple rather the differential equations of an ideal transformer by simple complex algebraic equations in order to infer what the phasors of the current and voltage are going to be. So, we of course, one of the important points which you should remember that this transformation to algebraic equations here, this works quite well for sinusoidal steady state conditions, but we have to be a bit cautious when we try to apply this when there are in fact DC currents flowing, etc. So, please be careful, do not apply these for any general situation. You have to actually check out whether this applies during sinusoidal steady state conditions. This of course brings us to a related concept called magneto-motive force. If actually I take the equations which are which we just wrote down some time ago, and we multiply both sides by N1, then we can in fact write it in this fashion, and these are in fact what is known as the magneto-motive force. So, magneto-motive force is the reason of course we call it magneto-motive force is pretty obvious. After all, the currents in the coil cause the fluxes. So, you know, the motive for having a magnetic field is in fact the magnetic MMF, magneto-motive force. Okay. Now, in case there is no load, then the magneto-motive force is simply N1 IOC, which is in fact the current required to sustain a certain amount of flux, so that V1 voltage appears on the primary winding. So, this is in fact called the magnetizing current, although you know it is open circuit current. It also contains in fact some current due to eddy current effects and hysteresis, but if you neglect those, then this is in fact what is known as the magnetizing current, yeah, magnetizing MMF, I am sorry. Of course, if you assume that you are loading the transformer significantly, then this term becomes quite small, and in that case you have got this relationship. Okay. So, this is only if IOC is negligible with negligible in as compared to the you know the load current. Okay. So, that is one important point we should remember, that here when I say negligible, it is with respect to the load current. This is actually quite true in most large transformers, at least. The current, open circuit current, that is the current which appears on the primary if you keep the secondary open circuited, is much smaller than the rated current of the transformer. That is, if you load the secondary with you know have rated current flowing in the secondary winding, I2 is the rated value, then the IOC is typically, the open circuit current is typically much smaller than the rated current on the primary as well. So, this is an important point which you should remember. For a large transformer, compared to the rated load current, the open circuit current is small. Okay. So, the one should be a bit interpret this statement appropriately. If you are keeping the transformer nearly under no load, then of course, it is not correct to take IOC as negligible, because that is the only current practically which is flowing. Yeah. Now, one of the important thing which again we should remember is all these phasor relationships were derived taking the sinusoidal steady state equations of V1, the relationship between V1, V2 and I1, I2. Otherwise, of course, there is a differential equation which you know under sinusoidal steady state we can use algebraic equations to obtain the sinusoidal steady state, a fact which we used quite effectively when we studied sinusoidal steady state circuits. Okay. Now, remember, for a 3 winding transformer, you need not be limited to 2 windings. In this 3 winding transformer, where all the currents are entering, for example, for the first winding, if the current is entering this point, the current is entering this point and the current is entering this point. Okay. All the 3 windings, you know, this will be essentially the relationship which holds. Okay. This is not very difficult to prove, only here you will have to have V1, V2, V3 and I1, I2, I3. The relationship will now of course be you know mediated with a 3 by 3 inductance matrix, and you can actually prove this V1 by V2, V1 is to V2 is to V3 will in fact be N1 is to N2 is to N3. And using these relationship, one can in fact find out that this is in fact true. Okay. In this transformer, remember, if you are using the dot convention, you would be having it is quite easy to find out where the dots will be. So, in this the windings are wound like in this fashion, in this sense. So, what you have is goes round like that and comes out again and comes out here like this, and in this third winding it goes in like that and like this. So, what is you know where does the dot appear? One of the ways of you know if you call this A1, B1, A2, B2 and A3, B3, you can actually slide all these windings to a common limb and easily make out that in fact they are wound in the same fashion. So, the first winding is in fact wound like this, the second one is also wound like that, and the third one is also wound in the same fashion. So, this is A1, this is A2 and this is A3, and the equivalent of this is in fact all these 3 have got, these are all coupled 3 windings, and your currents are in fact taken in this direction. If you take them in this, if you take the convention to be this way, and I3, and this is V1, V2 and V3, then you will have in fact we will have V1, V2 and V3 is equal to a 3 by 3 L matrix, and you will in fact have d by dt of I1, I2, I3. This 3 by 3 matrix will be symmetric because as I mentioned some time ago, one can prove rigorously using the basic physical laws that the mutual inductances are always, the mutual inductances are equal, that is the off diagonal elements are in fact this matrix is symmetric, that the mutual inductance between winding 1 and 2 is in fact the same as the mutual inductance between winding 2 and 1. So, there is a symmetry there. Also, in case your currents are going, the voltages are measured like this and the current is entering from this point. If you are measuring your voltage, the potential of this point with respect to this point, and the current is entering the first point here, then one can also infer from the physical laws that this L22 and L33, if we take this convention for the currents and voltages, that this in fact will be, these will be positive numbers here. So, this is the interesting point here, and also in this particular case, since the sense of the windings is same, and we call this as A1 and this is A2 and A3, in fact, it is not very difficult to show that M also will be positive. So, all the mutual inductances also turn out to be positive. Okay. So, with this convention here and dot product sign convention, this is what we get. And again, if we see the MMF relationship here, you will find that this holds. Okay. So, remember this minus sign is because the currents are going into the dot. Okay. That is one important thing. Yeah. In general, for a n winding transformer, this will hold true. If IOC is negligible, then the equation is very easy to remember. IOC of course is the current which flows to the first winding in case all the other windings are open circuited. Okay. Motivate you to the fact that there are situations where you should apply these whatever equations we are there which we have with caution. Let us consider this very interesting circuit. In this circuit, you have got a sinusoidal source, and on the secondary this is a 2/3 20 115 transformer, and this on the secondary you have got a diode connected to a resistive diode and a resistive load here. So, this is an interesting circuit because although you have got a sinusoidal source, the response is not sinusoidal because of the fact that this diode is a nonlinear element, it rectifies. So, in fact, because it rectifies, you may in fact have we of course have to do this analysis very step by step, but the point is that you can have DC currents flowing on the secondary, and when you are applying DC currents, you have to be just careful before directly when you are considering DC currents, you have to just be that little bit careful when it comes to applying the MMF balance equations. Okay. So, remember that the MMF balance equations were for sinusoidal steady state. So, you have to just be a little bit but here you have a mixed kind of situation. Yeah. So, of course, you take a practical transformer and you can actually do certain tests. For example, this short circuit test, we apply a voltage of 9.1 on the primary, and the current which flows in the secondary comes out to be 8.42 amperes. Okay. And similarly, if you apply for the open circuit test, if you apply 115 volts on the 150 volt side, the amount of current flowing through that is 0.925 amperes. Okay. And the power which is dissipated is this. So, these are two important tests which you can do to obtain the parameters of the transformer. So, these in fact, just to clarify, this circuit is not the circuit which you use when you do these tests. Short circuit test means you are going to short circuit one side of the transformer. Okay. And open circuit test means you keep one side of the transformer open. If you keep the if you do an open circuit test, what you are going to see is in fact the IOC. Okay. So, by doing open circuit and short circuit tests, you can actually infer try to infer the parameters of the transformer. What you cannot infer, this is something you can just try to think about. The number of parameters here are R1, L1, R2, L2 and also this mutual inductance and RC. So, there are 4 parameters and you actually do not have as many measurements. In fact, you can't obtain, for example, all these parameters distinctly. So, what in fact you can make some approximations. For example, during short circuit test, you can neglect the current flowing through this. The reason is of course that this current is usually much smaller. When you do the short circuit test on a transformer, what you do is of course apply a small voltage to one side and short circuit to the secondary. The current is high, but since you apply a low voltage, you can restrict that current to the rated current of the transformer, that on the respectively on the primary and secondary, the rated current only flows. And if that is the case, you can actually find out the current which flows. This current here maybe is quite negligible. As I said, the open circuit currents are generally very small. So, what you are going to see is practically R1 and L1 and the referred value of R2 and L2 coming onto the secondary. So, just to draw this. So, when you do an open short circuit test, actually what comes is practically this. This is an ideal transformer. Remember the equivalent circuit, we take this as an ideal transformer. If you neglect the open circuit currents and do a short circuit test, this is what the equivalent of the transformer is. And of course, you can refer this R2 and L2 onto the primary by a process of referring, which we discussed in the previous lecture. So, this is R1, L1. So, you got R1, R2 into N1 by N2 whole square, and this is L2 into N1 by N2 whole square, and this is L1. So, actually through the short circuit tests, if you know this voltage and you know this current, you can in fact if you know the phasor values of voltage and current, which you can in fact, you can measure the voltage, you can measure the current, you can measure the power dissipated. The real power dissipated is in fact only because of R1 and R2. So, you can actually take out from the current the volt ampere as well as the power factor. So, in effect you can take out the current the current phasor and the voltage phasor relative to the voltage phasor, and in fact then you can obtain what omega L1 plus L2 into N1 by N2 square and is, and what R1 plus R2 is. Of course, you can't through this test get what actually R1 and R2 are separately. Okay. So, with two tests actually you can't get this many parameters. From the open circuit test, so short circuit test in fact will yield these two sets of parameters. So, you will not get L1 and L2 separately nor R1 and R2 separately, but one of the common assumptions we make is that it is split equally between the two windings, that is R1 and R2 into N1 by N2 square is in fact we assume that they are equal. Okay. This is a reasonable assumption to make because the cross section of the conductor of the primary and the cross section of the conductor on the secondary are again related in some way. Why are they related? Because the rated current on the primary and the rated current on the secondary are also approximately N1 by N2. We saw that if IOC is negligible, this is true. So, you in fact you can roughly say that R1 and R2 are going to be roughly equal. Okay, in a very rough fashion they are equal. Of course, it depends on the length of the turns and so on, okay, how they are wound, etc. Okay. But we can roughly think the cross section wise, certainly the primary side, if it carries more current, the cross section is larger. If the secondary side current carries less current, then its cross section is going to be smaller. Okay. But of course, resistance also depends on the length of the turns. So, how you have wound it also will matter. Okay. So, this is an important point which you should remember. If you are doing an open circuit test on the transformer, then of course, the current flowing is this drop is going to be negligible because the current is small, this side is open anyway. So, the current flowing is in effect will give you what these two parameters are. Okay. So, you can actually obtain the parameters of a transformer through these tests, not all parameters, but sometimes a combination of parameters. In fact, through the short circuit tests and open circuit tests, we can get the equivalent of the transformer, equivalent because I mentioned some time ago, the R1 and R2 all get referred to one side, that is what you can actually measure. Okay. So, this is regarding the transformer parameters. The reason why I talked about transformer parameters is that if I want to analyze this circuit, which I showed you a couple of slides before this, that is this one on the top here, I should know the parameters of the transformer. Okay. Remember that the short circuit and open circuit tests are not what done using this is a separate circuit. Okay. The one which is shown here is a separate circuit. So, let us now concentrate on this circuit. If you look at this circuit, it has got what kind of behavior can one expect? In fact, one of the things you will notice, if you take a a transformer which is of course not ideal, let's just I will just one by one consider certain non-ideality. Suppose of course, if this is small, okay, not 0, but let us say it is small, the leakage parameter, leakage and the winding resistance is small. So, what happens is the voltage appears across these windings. Okay. Let us assume also that IOC is small, that is the open circuit current is small. So, practically this sinusoidal voltage appears across this winding. Okay. So, if you have got a sinusoidal voltage appearing across, which is almost equal to the source voltage, then V1 by V2 is going to be, so if V1 is sinusoidal, which is going to be, suppose it is a sinusoidal source, then V2 is simply going to be N2 by N1 times V1. So, one thing you can be reasonably sure is that if you have got a 220 is to 230 is to 115 volts transformer, now you will have the voltage on the primary secondary is approximately this. So, so this voltage is going to be approximately the voltage which appears here is going to be approximately this. Now, because this is the voltage and this is something which is if the leakage parameters are small, leakage and resistances are small, you can be reasonably sure what the voltage across this winding is going to be, and therefore, what the voltage across this winding is going to be V2. If you apply this V2 to this diode rectifier circuit, your current is going to be like this. It is going to be a half wave rectified circuit. So, if this is the secondary side current, this is what is going to be my secondary side. So, this is V2 which is the secondary side voltage, and this is going to be, this is now reasonably sure, this is what we will get, there is no approximately this is going to be true. Now, one important thing which you will notice is this is not sinusoidal, it is periodic, in steady state this will be periodic, but this is not sinusoidal. So, what you have here is effectively a DC component plus a fundamental component, that is if this is 50 hertz, this will be plus harmonic components. Now, one of the interesting things, so what you have essentially is some DC current flowing through the secondary. Now, what is going to be the current in the primary? Now, can we use this relationship N1 by N2 roughly, even if we assume the open circuit current is small, that is the if we had kept this open, the IOC would be small, let us say it is negligible, then N1 by N2 is it equal to I2 by I1 of t? The answer is no, this is not true. In fact, this is approximately true for the fundamental phasor. This is something we try to understand earlier. If V1 is a fundamental phasor, then in fact this is approximately true, but this is not, this is something which we cannot say for sure. For example, this has got a DC component. Now, the question is, can a DC component flow through this the primary circuit? The answer is no. Let us say the primary current has a DC. If the primary current has a DC, then the voltage drop across the winding resistance will be a DC. Now, if the voltage across the winding is going to be DC, let us just look at what happens. Suppose I take this is the leakage, let us say this is an ideal transformer, let us assume IOC is negligible. So, this has DC plus AC. AC would of course means also harmonics. Now, if you apply KVL to this loop, this is the voltage which you are applying. The voltage here, can it have a DC component? The answer is no, because in case the voltage here has a DC component, that means the flux N into d phi by dt, which is nothing but d psi by dt, flux linked, has got a DC plus AC. Now, the point is that in case there is a DC, what will happen to the flux? It will continuously increase, because this DC, if you integrate a DC, it will just continuously increase. So, in steady state you cannot have, a steady DC on the primary side, because if there is a steady DC here, the flux linked will continuously increase and the flux will also continuously, so there is no steady state. So, this cannot have a DC, this is an AC. So, if this cannot have, this does not have DC, this does not have DC, then by KVL this cannot have a DC. So, there cannot be a DC voltage drop across this. Okay. So, if there is no DC drop across this, there is a resistance here. So, there cannot be DC current on the primary. So, the important thing is I primary or I1 cannot have DC. I secondary has DC. So, in fact, remember that di by dt has no effect, because di by dt is equal to 0. So, di2 by dt is equal to 0. So, in fact, it does not cause any voltage to be induced. Okay. So, in steady state, if I has a DC component, any of the I's have a DC component, they do not cause any voltage. Okay. So, the important thing is you can have a secondary side having DC current, okay, because of the fact that this is AC rectified, this causes DC current to flow. But on the primary side you can't have DC, because this cannot have this voltage across the winding cannot be DC, the source voltage does not have DC, therefore, this drop cannot have DC. If this drop does not have DC, you can't have DC current flowing through here. So, now the point is that the primary side voltage is this Vp or V1, the secondary side voltage is this, approximately true. The current on the secondary is half wave rectified, it has a DC component. As far as the AC is concerned, the 50 hertz AC, anything other than the DC, of course, the relationship N2 by N1 is equal to I1 by I2 holds. Okay. So, in fact, N1 by N2 is equal to I1 by I2 holds for sinusoidal steady state. So, in fact, it holds for also the harmonic components. So, in fact, this is of course assuming IOC is small or negligible. So, negligible compared to I1 and I2. Okay. So, if IOC is small, this is true for all the AC components. So, the AC components, in fact, so if you first of all remove the DC, if you remove the DC component, you will get this. I did not draw it very well, I am sorry. You know, the 0 axis should be somewhere here and not this. So, this is 0, this is the same as I secondary, this will be I primary. So, we can expect I primary to be in fact like this. So, let us just see what we actually get. What we actually get is not that, it looks kind of similar. When we actually did this experiment, what we saw was the primary current, the secondary current as we expected is like this. The primary current in fact does not look like this, it in fact it looks a bit different. So, where have we gone wrong in our reasoning? So, what we did was we simulated this circuit. So, what we have actually simulated this circuit without saturation first. So, what we did was this is a program which will be given to you along with your along with the course material. You can just go through it. We have actually numerically integrated the equations of these equations, the equations of the transformer. So, please go through this carefully. And once we run this, we will not run this because it takes a bit of time. So, what we in fact are going to do is, if you simulate this circuit, this is what we saw experimentally. If you simulate this circuit, yes, this is what you get. This is the secondary current, this is the 0. As expected, the current is a half wave rectified waveform. The source voltage is in fact sinusoidal, this is what you see. The DC component of this secondary current is shown here, the DC offset in the secondary current. This is not directly measured, this is just by finding the average value using Fourier analysis. Okay. So, this is DC offset which you get. Now, what we see is this is the primary, this is the secondary current in blue. This is the voltage. What I have added now is what through simulation we get as the primary side current. So, let me just get back to what we had discussed here. What we expected to see in the primary is the same as the secondary. So, IP is nothing but N1 IP is nothing, oh I am sorry, here in this I did make a mistake, this should be I1 by I2. Okay. So, what you have is in fact I1, but this holds only for the sinusoidal steady state. Okay. So, the DC, you have to remove the DC offset because of the fact that I told you some time back that you cannot have DC current on the primary. So, you remove the DC and this is how the current would look like. I will redraw it. It is just a scaled value. So, this is the primary side, this is the secondary current which is half wave rectified, and the primary is simply the same waveform which is scaled by N2 by N1, but with the, I have not drawn it very well, but okay. This is just this minus the DC component. So, this goes down. Okay. But what you notice here is of course that when we simulated this system, what you get actually is something like this here. This is not a straight line here. Yeah. Why is that so? Because IOC is not negligible. So, what has happened is that IOC has got superimposed on this. Okay. So, remember that this relationship here is with IOC negligible. In real life there is some IOC. So, that is a small sinusoidal component which has to be superimposed on this. So, so what you have got is a scaled value of the non-DC value of the secondary current. So, you have to scale it down by this DC component and then add IOC to it to get what the primary current is going to be. So, this is what our simulation says. So, if you look at the simulated current in fact is having a small, it is not straight line here, this is because of the fact that there is some open circuit current, I mean the magnetizing current is not negligible. Yes. Now, so in fact we can infer how much is this IOC by simply subtracting the primary minus the secondary current, primary minus in brackets the secondary current minus the DC offset divided by the turns ratio. So, if you do that you will in fact can infer what is the open circuit current. Okay. But what we expect is of course the primary current should be what is shown in red here through simulation, but this is not what we see. In fact, if you look at the waveform, It has got a much steeper jump here. Now, why does this occur? Remember that if you model saturation, why does saturation occur? Remember that if you have got this 2 winding transformer here and you have got a DC current flowing here, and the flux in the core, because of the fact that the DC current does not kind of get reflected on the AC on the primary side, although it exists on the secondary side, it does not get reflected on the primary side. There is a kind of the flux in the core is in fact not sinusoidal, but has got DC plus AC. Now, what happens because of this, if you take the flux versus current flux linked versus current relationship, say this is the flux linked with the primary winding and this is the the flux current relationship, this is the total current, that is the primary side current plus the MMF in fact, N primary plus Ns secondary. You will find that in fact since the core is nonlinear, what happens is that the flux and the current are linear up to certain point. There is a hysteresis also, I have slightly exaggerated the hysteresis. So, normally you are working in almost the linear region. So, this is if you are AC, you will go traverse both positive and negative, you will go positive as well as negative. Okay. So, you will go in this quadrant and this quadrant. Now, if you the hysteresis is slightly exaggerated, for cores of this kind the hysteresis is usually small. Now, the thing is that because of the fact that there is a DC flux, what happens is normally if you got AC, just AC, the flux level in the core goes from is kind of traverses a kind of symmetric path in both quadrants, this quadrant and this quadrant. But because of the fact that you have got DC, now you are operating practically, say you are offset. So, you are in fact operating in this region now, and in this region at some point of the sinusoidal curve you will get saturated, as a result of which you will require a large amount of current to set up the flux. So, we can no longer use the linear model to actually infer this. So, in fact, if I do a simulation and I in fact try to model saturation, which I have done in the program which is will be put as a part of your materials, you will find that this opens this current which is also called a magnetizing current, this component here, this yellow component here, to set up the flux you really require some part of the sinusoidal cycle you will really require to have much larger current to set up the flux, because you are now offset and entered the saturation in one part of the sinusoidal cycle. Okay. So, that is why you will find that in fact you will get this kind of peaky nature. So, if you actually numerically integrate these equations, you will actually understand why this is happening. So, please use these programs and run them and see that you are in fact getting. So, this now looks very much like what we saw during in the experiment. So, actually we have replicated this this circuit, which is an interesting circuit, by simply numerically integrating it. But what you get as a result is in fact, if you consider saturation, you are able to replicate the results quite well. Why do you get saturated? Because although you normally operate symmetrically, in the psi versus I kind of characteristic due to normal AC conditions, because of DC you have actually moved up or possibly moved down. I have not really checked this place where it goes, the offset, whether it is positive or negative, but that is something you can try to analyze. But you go on one side, so that much is certainly true. You go on one side and because of that on some part of the cycle, because of the nonlinearity, you require much larger magnetomotive force to set up a flux in the core. Okay. So, that is why you enter a nonlinear part of the psi I characteristic, and therefore, you will find that you are getting a kind of peaky curve here. So, you can in fact do this experiment in your laboratory and also run the numerical simulation to satisfy yourself. Now, we move on to another interesting topic. Before we go on to what is an autotransformer, one of the interesting thing a transformer allows you to do is in fact provides what is known as isolation. Now, what do you mean by isolation? Well, actually there is practically no electrical connection between the primary and secondary sides of a transformer. So, if you have got for example, a transformer like this, there is a very high impedance between the windings, they are insulated from each other. So, the insulation resistance and intra turn capacitances which are there between the windings. Okay. So, there is a kind of capacitance between these two windings and also the insulation resistance. So, there is an impedance between the windings which is quite high, very high. So, actually there need not be any current flow between these two. So, if you have got a say a sinusoidal source here and a load here, actually no current traverses this because this impedance is very high. Only due to induction the voltage is induced and a current flows here. Okay. So, there is no direct conductive coupling between these two sides, and this is very useful because what it means is that I can suppose I have got a source like this and I connect it to a resistance. Okay. Now, what the current will of course be dependent on V and R, in fact it will be V by R. So, if the current will be equal to V by R. Now, the current. Now, suppose I connect this point to the ground, okay, the earth. Okay. Let us say it is a very nice connection. So, there is hardly any resistance here to the earth, the electrode is a very nice electrode, and I also connect this to ground. What will happen? Since this is connected to ground and this is connected to ground, for all practical purposes, if you neglect the resistances of the ground, you have connected this point to this point. So, you have shorted out the resistor and the current will become almost infinity. So, I cannot just take 2 points and connect them to arbitrarily. Okay. So, I can't just connect this to ground and this to ground, this will actually cause a short circuit. So, I am not at liberty to do that. Of course, I can do this will not create a problem because this is anyway, even if I short it, there is a metallic connection here. So, this will not affect the circuit. Okay. But in fact, with a transformer you can do this. What can you do? If you have got a transformer, the same circuit, let us take a 1:1 transformer, I have got a resistance and I can actually ground this point and I can also ground this point. Now, the thing is that this is effectively connecting this point to this point, but does it affect the circuit? The answer is no, there is no return path for this current. What will happen is of course, there is a kind of impedance between this path because of the insulation resistance as well as the capacitance between these turns, but this is an extremely high impedance. So, for all practical purposes hardly any current flows through this. Because no current flows through this, for all practical purposes having this connected here will not affect the original circuit. So, this if you connect the grounds here does not matter, you can connect the ground here also. Well, you can't connect it both at the same time, but if I get, for example, I remove this and I connect this to ground, this also will not affect the circuit. So, you are absolutely liberty to connect one ground either here or any other place. Okay. So, any one of the places you can connect without affecting the overall circuit. So, this is a interesting application of a transformer. It gives you isolation. Why do you require this isolation? For example, you have got an electronic circuit, the electronic circuit is derived from a power supply, the power supply is grounded at some point. So, the voltages you are getting at the output, for example, typically your source is between line to neutral. So, the voltage which is we are getting here are in effect between line and neutral, and the neutral is grounded somewhere usually. For example, in most power supply systems, in most of them the neutral is grounded at the source. Okay. This single phase is derived from a 3-phase where the neutral is grounded at the source. Effectively what you are getting is the voltage, voltage at this point, its potential with respect to the earth has been defined in some ways. It is somewhere there is some connection of this potential with the ground. In some circuits where this may be required, that in fact this is very common in what are known as power electronic circuits. The power electronic circuits is a high power circuit, some point of it may be grounded, okay, or is related to the ground potential in some way, because the power circuit also is fed from some circuit which has got connections to ground at some point. You have got another circuit which is giving a signal to this power electronic circuit, say the switches to switch on or off, that also is grounded. If you just connect them together without isolation, it is possible that inadvertently you have made some connection from one point on the power circuit to the signal circuit, and sometimes it may create a problem. A prime example is here where effectively it gets it causes a short circuit. Okay. So, under such circumstances these kind of situations do not occur normally, but you can actually provide an isolation between the signal circuit and the power circuit, or signal circuit A and circuit B, and keep them isolated through a transformer. Connecting them together with a transformer will not cause inadvertent current flow, as I have shown you in this case. So, there will be no inadvertent current flow. If you have isolation, there is no danger of this happening. So, in certain circuits it is important to have this kind of isolation. Transformers is one way you can have isolation. The other way to have an isolation is using optical circuits, where the signal is actually conveyed from one part of the circuit to the other part of the circuit, not electrically, not through a conductive kind of electrical connection, but through light signals. So, that is essentially radiation, which you can, and you of course have to have sensing elements on the circuit B, and circuit A will have to have a light emitting circuit. So, you can actually send signals from one circuit to the other without having any electrical connection between them, a direct conductive connection between them. A transformer allows you to have a non-conductive kind of transfer of power, non-conductive transfer of signals, and this is useful under many circumstances. You can in fact, an interesting thing, an interesting transformer connection is also possible where you have a conductive coupling, and obviously as under such situations isolation is lost. For example, you take a transformer, let us say it is a 10 volts is 200 volts transformer. Now, I deliberately make a conducting, make a different, means I make a kind of connection to this transformer. What I do is I take this 10 volts, this is a normal 2 winding transformer, I take this 10 volts. What I do is now I connect the 100 volts like this. So, I connect this bottom point here to the top point here. Okay. Now, if actually I connect it in this way and I connect it to two different sources, again there will be no current flow because the impedance between these windings is very large. But if I in fact connect this point and apply the voltage here, now I have lost my isolation because now I have connected at 2 points. Of course, if you connect it at 2 points, you will certainly lose isolation. For example, in this case, this is an isolated circuit, but if you actually connect it at 2 points, then we will lose isolation. For example, if I connect it here and here, then you will have this connection here, or if you have got, so now there will be all kinds of connections, So this, so the point is simply that isolation can be ensured if you, you have to do it carefully. I mean, you can connect one point to ground and this point here to the ground. This is still an isolated circuit, okay. But now we do not have isolation because I have connected this point to this point and also connected this point to this point, okay. So the potentials on both sides are related. So now these two sides V1 and V2 are not related, rather they are in fact not isolated, okay. Now if you look at this, suppose this is rated at let us say 10 ampere here and the rating of this winding is 1 ampere here, okay. this is 10 volts into 10, this is 100 into 1. So, the volt ampere rating on primary and secondary is equal. We assume the magnetizing current is very low. So, N1 by N2 is equal to I2 by I1. So, if the rating is 1 ampere here and it is 10 ampere here, it is interesting to see that using this transformer you can actually get a 110 volt, you can apply 110 volts. This is this N1 is to N2 here is 1 is to 10. So, this is, if this is 1, this is 10. Okay. So, what you will have is 10 volts will appear here and 100 volts will appear here. Okay. So, none of the, you are not exceeding any rating, 110 volts is applied here, and I have just reconnected this transformer in this fashion, and you will find that 110 volts can be applied to this reconnected transformer, and you can have in fact 10 ampere flow here, and you can have in fact 1 ampere flowing to this. So, you can have 10 ampere flowing here, and in fact what you will have here is 11 amperes, because 1 ampere flows through this. Okay. So, now what you have really done is that with a 2 winding transformer you have got a 110 volt is to 100 volt transformer, and the primary side current can be 10 amperes, the secondary side current, secondary I mean what appears in the at this point, there is a junction here of course, the current through this is still 1 ampere. Okay. You will still have 1 ampere, if 10 amperes flow here, 1 ampere will flow here, because N1 by N2 is still 10, so the N2 by N1 is still 10. But the current flowing out of this junction here is 10 ampere plus 1 ampere is 11 ampere. So, what you will have is none of the transformer principles are being violated here, that is important. None of the transformer principles are being violated, but using this simple connection you have got 100, effectively you can handle now here you could handle 100 volt ampere of power transfer. Now, you have got 1100 volt ampere. So, what you have achieved here is by this connection is in fact a very you are really having a much larger rating of the transformer. Of course, some of the current is simply flowing here, 10 amperes of this is simply flowing from one end to the other. So, there is not exactly transform the current. So, this kind of connection comes at a price. This is not isolated in the sense that I cannot connect now this to ground and this to ground, this will create a short circuit. So, you can't do that. So, isolation is lost. This kind of transformer connection is called an auto transformer connection, does not have isolation, but is used whenever you can actually show that this works out well in case this voltage is near this voltage. You will get a quite a large your rating of the transformer kind of increases very significantly by converting it from a 2 winding transformer of this kind to an auto transformer connection. But what you lose in the process? You use your isolation. So, in fact auto transformers are used in a power system whenever you need to have small transformation ratios. For example, from 220 volt to 400 kV you use an auto transformer, okay, but you lose isolation. Okay. So, that is an important thing. To illustrate the loss of isolation, let us just look at the auto transformer essentially was the connection I showed you just some time back. Yeah, here it is. Okay. Here you do not have isolation, you cannot ground points here and here arbitrarily. Okay. Of course, you can ground this point and this point because these are anyway at the same potential, but you can't connect for example this to ground and this to ground, that will effectively make a short circuit path here. Okay. Yeah. So, just to show this just a nice experiment here. Suppose you have got your 3-pin plug and you use an auto transformer and you connect this to a rectifier, and what you do is I ground this point of the rectifier, okay, the negative bus of this rectifier, and well, I do not ground it, I connect it via resistance to the earth point. Okay. Now, the point which I would like to make through this, suppose I keep this open. Okay. If I keep this open, then this circuit in fact is connected from line to neutral via this auto transformer. So, this is the neutral potential and this will be the line voltage, but it is scaled by the depending on the number of turns above this and the number of turns below this. And this voltage I apply to this rectifier. Rectifier means not all these switches are on at the same time, the diodes get on whenever they are forward biased. So, actually the potential of this point here with respect to this point keeps changing depending on which switch is on. Okay. So, depending on which of these switches is on, the potential of this point with respect to this point keeps changing. Because this changes, this may change. Now, the thing is, if I try to do this experiment, the current waveforms which I get are as seen in the next slide. As expected, the DC voltage is a rectified sinusoid, it is not really very sinusoid because the voltage in the laboratory is not very sinusoidal, but more or less rectified sinusoid, and the current is simply proportional to the rectified sinusoid. Okay. So, because the current is simply IDC is nothing but V naught by R. Okay. So, what you find is of course is that the current is this way. Now, there is negative bus is not earth. If I connect the negative bus, this I connect. Now, if current flows through this, what can I say? If I short this and current flows through this means there is some current flow means it affects the circuit. So, the point is that by connecting this I affect the circuit. So, what do we actually see? Does it affect the circuit? Yes, because I measure this earth current, what is shown here is yellow, and you find that the earth current there is indeed a current flowing, there is indeed an earth current flowing if I connect the negative bus to the earth. So, the point is that in this circuit you cannot connect this point arbitrarily to the earth. Okay. This is an important point. Why does this happen? Is there a return path? The answer is yes. You see that this current flows here, goes into the earth, but most of our 3-phase power supply systems, remember the single phase supply is derived from a 3-phase supply, and at least in a laboratory the power supply which is coming from the utility, the 3-phase power supply is grounded at the source point, the neutral is grounded. So, in fact, there is the current will flow and enter the earth and come in or earth conductor and actually get connected to the neutral somewhere near the source. So, there is actually depending on the nature of the 3-phase connections and earth connections, there is indeed a connection between the neutral and earth. In our laboratory, the power supply which comes, the neutral is in fact practically at the earth potential, okay, because the neutral is earthed somewhere. Okay. So, as a result of this, connection of this point to the ground through a resistance in fact alters this circuit. It alters this circuit because this and this is connected, and now you have to use KVL and KCL and you can really show that there will be some current flowing through this. Okay. So, an auto transformer in fact does not give you isolation. If you try to connect this to ground, because of the fact that N and E are also connected at some place in the power supply, the power supply which comes to a laboratory, you will find that in fact there is some current flow. Now, so this is what is illustrated. You have current flow for some parts of the cycle if you have got a negative bus earthed, and of course, because of this alteration of this circuit, because of the connection, what you have is that the voltage, actually in fact the mean value of this voltage slightly drops. Okay. So, in fact, what you see before is around 60 and this becomes 59. Okay. So, there is small change there. So, that of course depends on what resistance value you put here. It depends on the value of resistance and all the impedances here which are part of the source. So, I can actually redo this experiment now with a transformer. I take a 1:1 transformer So now of course there is no, the return path is through a very high impedance path, and therefore no current will flow through this, and because this is isolated with the transformer, you are at liberty to ground this point. Okay. So if I connect this, of course in this case there is the current on the DC side is as before, and there is no earth current, okay, because of the isolation. So you can also try this experiment using a transformer, and you will see no current is flowing through this even if you switch on this. So this is an interesting aspect about isolation. Of course, I mentioned to you in the previous lecture that in fact most of the transformers which we use are in fact 3-phase transformers for power supply systems. So we will just have a look at what are the kind of connections you can have in a 3-phase transformer. Remember, you can have a bank of 3-phase transformers connected to each other, but remember that the return path can be common, the neutral path, you can have a star connection with a return path. The advantage is, of course, if you got a balanced system, the return current through all 3 phases kind of cancel out in case they are merged into one, because IA plus IB plus IC is equal to 0. Of course, it is not true always, but usually the neutral current can be kept, it can be smaller than the individual line currents, because they usually cancel out if the load is reasonably balanced. Okay. You cannot ensure balance always, but as you go upstream in a power system, because of approximately you will find that the loading is similar on all phases. In fact, it is designed to be that way. So as you although this is kind of statistical, it depends on who switches off which load and so on. Mostly the loads are balanced as you go upstream, as you see from an upstream 3-phase system. Okay, because on the average you will see that the load is more or less the same in all the 3 phases. In that case, the neutral current can be quite low, and therefore the current through a neutral wire can be low upstream in a 3-phase power supply system. Not right at the load, because if you have got one building, and it is very possible that all the 3 phases are not loaded equally. But if you aggregate it, then on the average, yes, that kind of works. Okay, yeah. So if you look at a 3-phase transformers, you can apply the MMF balance to these 3 single phase transformers. The equations are, in fact, in case the open circuit current for all the 3 transformers is negligible, then you will have this relationship for all the 3 phases, and these 3 transformers then this is a bank of 3 transformers. You can connect them in what is known as the star and delta connection. So can we go next? Yeah. So what you are shown is, in fact, the primary and secondary in fact can be connected differently. You can have one of them, for example, here both all the 3 transformers are connected in star, that is, the primary windings are connected in star and the secondary windings also are connected in star. And if you have this kind of transformer, then it is not very difficult to see that the voltage across the line to line voltage VAB is in fact equal to it will be equal to the turns ratio times VAB2 will be the turns ratio N2 by N1 into VAB1. There will be no phase shift because because the connections are exactly similar on the primary and secondary transformers. The line to line voltage is, in fact, there is no phase shift. This is called a YY transformer, and because the neutral point is shown here to be grounded, it is usually called a neutral grounded transformer. So YN grounded. Okay. You can also have what is known as a star delta transformer. The primary secondary side voltages are connected in delta. What you notice, of course, is now the line to line voltage ratio is not equal to the turns ratio, because if you notice on the delta side, the voltage across the winding appears across the line, whereas in the primary side the voltage across the winding is not what appears in the line. In fact, the voltage across 2 windings, the difference of voltage across 2 windings in fact is what is VAB. So VAB is actually VA neutral minus VB neutral, yeah. Whereas here you find that the voltage across the phase, one winding of the phase is what appears across the line. Okay. Line to line voltage in a in the primary, the line to line voltage is root 3 times in magnitude of the phase to neutral voltage. Okay. So, if the voltage across the winding is say 230, then VAB will be, the magnitude will be 230 root 3 in a balanced situation. In a balanced situation, VAB will become 230 root 3. This is something we learned when we did 3-phase systems. Okay. Whereas here, suppose it is a 1:1 transformer, that is the turns ratio is 1:1, that is each individual single phase transformer which forms a part of this bank of 3-phase transformers, each individual transformer says the turns ratio is 1:1, then what you will find is that what appears here is going to be 230 volts. So, you are going to get 230 volts here, and on the primary the winding voltage is 230, but the line to line voltage will be 230 into root 3. So, the line to line voltage ratio in this case is 230 root 3 is to 230. Okay. So, if it is a 1:1 turns ratio. So, remember that there is a distinction now between turns ratio and the line to line voltage ratio. Yeah. One more thing is of course the phase shift. The voltage, line to line voltages on the primary and secondary are not in phase. For example, in this case, I will represent the voltage phasor. We call this we have discussed this sometime in the previous class. We will take the clockwise direction as positive. So, VB lags VA by 120 degrees and VC lags VB by 120 degrees. Okay. So, if you got this kind of transformer connection, it is quite easy to see that since these are complex numbers, you can take out the VAB as, and this comes out to be in fact of magnitude. If this is 1, this will become root 3, and the important thing is that there is a 30 degree. So, VAB is like this and VA is like this. So, there is in fact a 30 degree lead of the line to line voltage on the primary. In this case, the line to line voltage on the primary VAB, sorry, this is VAB is going to be 30 degrees. So, line to line on primary is 30 degrees leading phase to neutral or line to neutral voltage on primary. Okay. What about the secondary? The secondary, so I will just redraw this. This is how the primary looks like, and in the secondary what we are seeing is VAB is nothing but, I just slightly increase this. Okay. So, VAB is nothing but the voltage across the winding which is shown here, this, and this, if you take a 1:1 turns ratio, then this is simply what you get here. Okay. So, this will be simply equal to this if it is a 1:1. So, VAB will be simply this voltage, and this voltage is simply going to be equal to this if the turns ratio is 1. So, what you have here is, this is the line to line voltage which you will get here, and the line to line voltage here is like this is the primary, this is the secondary. So, this is VAB on the primary and this is VAB on the secondary. So, VAB is in actually is going to be in the voltage which is in fact is minus VAB, I am sorry. So, what you have here is going to be minus VAB. So, since you have connected this, it is not VAB, this is VB, this is VA. Since there is the 1:1 turns ratio, this is VB on the, this is the voltage induced from this potential of this point with respect to this point, but VAB is measured like this on the secondary. So, what you have is in this direction it is minus VAB. So, in fact, you will have this as VAB. So, the secondary on the secondary the voltage is like this. So, in fact, it is not difficult to show that if the VAB primary is like this, VAB secondary is 30 degrees leading it. So, you will have in fact a 30 degree phase lead of the secondary line. So, line to line voltage on the secondary leads the, in this case, you know, even if you may have got confused. So, you can try to rework it again on your own. You can surely show that VAB on the secondary leads the VAB on the primary by 30 degrees. Okay. So, in fact, by connecting it in different ways, for example, and naming it differently, you can get different phase shift. So, as a simple exercise for you, try to obtain the phase shift between VAB and VAB on the primary and secondary in this circuit as well. Okay. I also have a few more interesting experiments on harmonics and nonlinearities of 3-phase transformers, but we will do this in the next lecture.